Hi, I'm Eric. In this video, I'm going to introduce you to my final project, a self-balancing robot. Many of you know self-balancing robots very well or even have experiences riding a self-balancing robot like the Segway robot. Thanks to the advances in robot control series and cheaper electronic components, self-balancing robots also gain popularity among the research community. For my project, I bought an Arduino self-balancing robot kit. It has 2 wheels and it is unstable and underactuated. Let's first talk about things that we're all familiar with, the Segway robot. The modeling of the Segway robot can be very complex. After referencing a paper modeling of 2-wheel self-balancing robot driven by DC gear motors, I simplified the model by making the assumption that the robot is simply an inverted pendulum with center of mass concentrated at a single point with distance L from the wheel. Based on the simplified model, the dynamics can be described as shown. Note that there are some nonlinear terms like cosine sines. Assuming when the robot is stable, the pitch angle and the velocity is small. So cosine theta is 1 and sine theta is theta, and theta dot squared is simply 0. Then we have this linearized system as shown below. While on a more advanced robot I might be able to directly control torque, on a hobby level robot I need to control the DC motor directly, so actuator dynamics come into play. On the seller's website, I found a datasheet of the motor and converted it to SI units. Then, assuming the inductance is negligible, I fitted a line to figure out the winding resistance and motor constant Kv. Kt is found directly by dividing the rated torque by the rated current. We also need the motor angle and the velocity for 2 reasons. 1 is in the robot dynamics, and 2, we also need it for actuator dynamics. There's a 2-channel encoder with a base resolution of 11 CPR on each of the motors, and we can use 4 times resolution to get an equivalent of 44 CPR. For wheel angles, we also need to divide by the gear ratio. From the previous method, we can only get the angular position. To get the angular speed, we can apply an IIR filter like the one we used in the lab for a smoother velocity. The raw velocity value might have a lot of high frequency noise that can be removed by the low pass filter. And finally, to control the motors, the robot kit used an H-bridge. Unlike the advanced H-bridge in the hopping leg, the H-bridge that came with the robot only controls the motors by PWM and has no current sense. To get the voltage applied to the robot, we could use the root mean square voltage, and we can get the current and torque by the formula on the bottom right. For the pitch angle and velocity, I used the IMU on the robot. Based on the acceleration in the X, Y, and Z directions, I could figure out the pitch angle by the formula. And the gyroscope directly provides the pitch velocity. However, I still needed to apply a Kalman filter on the angle and velocity, or otherwise it would be too noisy. After combining the robot dynamics and the actuator dynamics, the combined robot dynamics is shown on the left. I first implemented a very simple PD controller as described in the formula. A more common approach in research is to use a linear quadratic regulator, or LQR, to control the underactuated robot. Referencing the paper, I define the state and convert the dynamics into an x dot equals ax plus bu form. The goal of the LQR controller is to minimize the cost defined as J below, while staying in the system dynamics constraints as shown in the previous slide. For the cost weights Q and R, I weigh the pitch angle much more than the others. In conclusion, PD controller is more generic, and the LQR controller performs better on the self-balancing robot. The main limitation of the LQR controller I implemented is that it has no ability to turn, since I mounted 2 wheels together, so it's something to improve on in the future. Another takeaway is that there are noises in real environments and filtering is the key. Here are the references. Thank you for watching.